Welcome everyone to this new appointment of the 40 under 40 lecture series on combustion. Today we host Dr. Lu Tian, and I'm very happy that she accepted our invitation. She's a lecturer in sustainable transport technologies at the Department of Aeronautical and Automotive Engineer at Loughborough University, and she's also an honorary lecturer at the Imperial College in London. She obtained her PhD degree at the Imperial College in 2018, and her interests include the CFD modeling of alternative fuel combustion in laminar and turbulent flows, the predictions of gaseous and soot emissions, as well as the flame synthesis of functional nanoparticles. In 2024, so recently, she obtained the Isherwood Prize by the Combustion Institute, the British section, in recognition of her work in combustion. And she was the first Asian woman to receive this award since its installment over 20 years ago. Dr. Tian was previously also a receiver of the prestigious Imperial College President's Scholarship and was shortlisted for the Osborne Reynolds Award and the Institute of Physics Lefebvre Prize. Today, she will talk about ammonia. Ammonia as a fuel, perspective on emission, mitigation, and modeling consideration. Again, thank you very much for having accepted our invitation. I give you the floor for your lecture.
Thank you, Alexandra. Thank you for inviting me. Thank you for the, the whole organizing committee to invite me to give this lecture about our recent work. And thank you for our audience to join us today. Today, I will talk about the work that I've done in the past 2 years about ammonia combustion. So I'll go to the presentation mode here first. So if there's anything wrong, just please shout out. I know that we have a Q&A session in the end, but if you have any question before that, just feel free to ask. I'm just going to make this smaller so I can see the screen better. That's okay. Okay, so what I'm going to talk about today, so I call it perspectives on emission mitigation modeling considerations, is because most of my work are computational based. So what all of this ammonia combustion work I'm presenting here are based on simulations. So that's why I say modeling considerations. Let's talk about some background first. So all of us here would understand why we are doing, net zero fuel combustion is because we have this urgency to achieve net zero carbon emissions by 2050. And we have a lot of applications that cannot be fully electrified. For example, we have the hard bus industry, such as heavy-duty trucks, marine applications, and some energy generation applications. So all of these applications are likely to need alternative fuel in the near future. So our question would be, which fuel do we want to use for these applications? So we have multiple choices as an alternative fuel. Each of them have pros and cons. We don't have a definite answer to this at the moment. What I'm going to present today is just about ammonia. But I just want to list some topical top candidates as alternative fuels. So maybe later on we can have a discussion about which one you want to research and work on more. So we have ethanol, biomethane, hydrogen, ammonia, and methanols as some of these most topical candidates for alternative fuel. So they can be made from different resources. For example, we have ethanol, biomethane. They can be made from biofuels, organic matters, and we can make hydrogen, ammonia, methanol actually together in the same site using different kind of methodologies, including some sort of renewable production methodologies. We can use water electrolysis to make, for example, hydrogen and make ammonia and green ammonia and methanol after we make green hydrogen. So that is to say, we have a future of producing ammonia in a green fashion. So that is the very key point. And the second of all is why we are going to do ammonia. What is the history of ammonia? Where did we use ammonia before we actually burn it in an energy application or in an industrial burner application? So before that, ammonia has a great applications, like perhaps all of you have known already. So ammonia is industrially produced in large quantity before. It was for fertilizers and chemical products predominantly. And so therefore, there are a lot of benefits because of these. I'm going to show it on the next slide, because you have a great network already on which we can use it to transport ammonia as a fuel. And we all know that ammonia contains hydrogen items, so it's a promising hydrogen carrier. So the motivation of burning ammonia rather than hydrogen is that we can transport ammonia already. Why do we need to convert it completely to hydrogen? Can we just burn it as a fuel? So that's the biggest motivation. And how can we do this? There are definitely challenges that we'll talk about on the next few slides. So before I do that, just let me show you this graph. You may have seen this already multiple times to people who actually do ammonia. This is just to say, apart from the good ways of producing it in a green fashion, we also have a great network of transporting ammonia across the world from one place to another. As you can see, it's actually connecting different major points across different continents. So this is a good thing. It is a basis for our research of doing ammonia. This shows it has this great potential of moving ammonia around the world if we can produce ammonia in large quantity. So the second question is, okay, we have this infrastructure, and how do we burn it? What are the challenges of that? So before I talk about, this is just one slide about the histories. Like, in the interest of ammonia is not just starting in the recent years. Actually, about several decades ago, and people have some interest about ammonia already, especially in the US. For example, these are some examples. For example, 1914s, and there is ammonia and coal-powered bus in Belgium. And then there is some other studies to actually study the ammonia gas turbine invested in the US. And also there's a combination of ammonia and liquid oxygen rocket motor that people investigated in 1967. You found that's the period where people are quite interested in aerospace applications. So that's being applied to gas turbines or hypersonic aircraft. And now, and then the interest decreased as people meet difficulties. And then in the recent years, the interest of ammonia came back again. So we want to just use ammonia as in our traditional, for example, internal combustion engine and so on. And then can we do this? What are the challenges? So let's just move to the next page and talk about that. Since I believe most of us are here are actually doing combustion, so I think we are quite clear about the advantage and disadvantages already. But if you don't mind, I just want to just talk us through this a bit again. So for example, why we're doing ammonia? Because it saves costs for hydrogen storage. It's difficult for hydrogen to be transported, stored. So we transport ammonia instead. If we burn ammonia, that saves the cost for transport hydrogen otherwise. It has material synthesis technologies. We have method even to produce it in a green fashion. And it's carbon-free, so it's NH3. It doesn't have a carbon element within it. So we consider that's kind of environmental benign if we consider carbon dioxide pollution. But we will talk about something else. Then it comes to disadvantages. For example, ammonia, it burns very slowly. It has very slow laminar burning velocity. And so because of the presence of nitrogen element within ammonia as a fuel, it can potentially generate high nitrogen oxide emissions, or we can just call it NOx, so which is not pleasant either. We don't want it. It can be bad for our environment. It can be also bad for human health. And the third of all, ammonia itself is toxic. So even a small amount of it goes to the human body can hurt people's health as well. So we don't want to have a lot of ammonia left in the end in the exhaust pipe. So we don't want residual ammonia either. So people call it ammonia sleep. So we want ammonia to burn more easily, we want less NOx, and we want less ammonia sleep. So that's how we want to do and to overcome the disadvantages of burning ammonia as a fuel. So how do we do it? So people have come up with different strategies to just solve these disadvantages. What I'm going to do is going to talk about the 3 most recent works that we have recently done. So which are trying to look at how we're going to tackle these disadvantages and what are the model considerations when we are simulating the ammonia combustion flames. So the first thing is, okay, so ammonia is very difficult to burn. So in a lot of studies, we just mix ammonia with hydrogen, and we rely on the characteristics of hydrogen to help the ignition of this fuel mixture. And the second of all, some of us argue that we have the hydrocarbon fuels are not necessarily fossil fuels, because now we have a lot of hydrogen neutral fuels that has hydrogen carbon element, but they're not from fossil fuels, they're made from renewable sources. So there is also a potential of blending ammonia with a hydrocarbon fuel. But that question comes to us is if we bring the carbon element back to the fuel, it may generate soot. So that's the second work we're going to look at, how ammonia affects soot formation. And third work I'm going to look at today is how we're going to increase the chance of ammonia being burned. Is like we can crack it into a mixture of nitrogen and hydrogen, but we don't want like a fully converted to nitrogen and hydrogen. Otherwise, that would be burning a hydrogen effectively. So just looking at a particular cracker ratio and we're going to look at if we can reproduce the results from experiments. So these are the 3 works that I'm going to talk about today. Okay, so before I talk about the details of my work, I'm just going to have these slides. It looks a lot of information, but I'm not going to go through a lot of details, because for the 3 works, for all the 3 works, there are turbulent combustion simulations involved. For all of these turbulent simulations that I've done, they are based on transported probability density function method. Just in case some of you may be not quite familiar with the method, so this slide just serves as a purpose, as the introduction to the method. So the transported probability density function method, it consists of a lot of different like subcategories. We can solve the scalars, for example, the mass fractions of different species and enthalpy using this transported PDF method. We can also solve both the velocity field and the scalar field using the transported PDF method. For the work that I have done here, I used joint scalar transported PDF method, which means for the velocity space, if I can bring my pointer out, that would probably be easier. Just spare me a second. My pointer is not okay. If I can use my mouse, can you see my mouse? Hopefully that will be fine. So the left-hand side is just to say, for my method, the velocity space is based on still based on finite volume method. So for example, we can use RANS, URANS, and LES to solve the velocity space. And the scalar space are based on the transported PDF method. So the mass fraction of species, enthalpy, and those information are solved based on transported PDF method. Well, the 2 different solvers needs to exchange information. So the scalar space gives the information such as density to the velocity space. Velocity space provide velocity, like velocity field and key parameters such as turbulent time scale and so on, and scalar dissipation rate and so on, back to the scalar space. Now, how do we solve the transported PDF method? There are different ways of solving it as well. And there are 2 major ways. One of them is to solve it in the Eulerian framework based on the stochastic differential differential equation method, and based on ether integral, and people call it Eulerian stochastic field method. And the other method is based on moving Lagrangian particles. I'm using the second one. So my method is based on moving Lagrangian particles. Basically means in each of these finite volume cells, I have about hundreds of particles moving around inside the cell, and it also goes to the next file, and the cells adjacent to it. It can also go across to a different cell according to the velocity that it has at that moment. So how do we solve it? So the particle here, the Lagrangian particle here, so what information it carries, like I just mentioned, so it carries the species mass fraction, it carries the, and also the enthalpy. So this equation is just the transported probability method, transported PDF equation itself. So how do we solve it? Based on the moving Lagrangian particle method, we have 3 steps to solve it. So I just listed separately, but it's not the way of us solving it actually in the code. So what we solve it first, we have the molecular mixing first, for example. We inside each cell, we choose, it depends on the model, but for example, I just gave me an example that in each cell, we just choose which 2 particles participate in the mixing, and or how much percent of particles participate in mixing, and how it actually makes and leads to the new properties for each particle in the end. So the second of all is chemical reactions. The best, or we say the most the advantages of using transported PDF is does not need us to create a model for chemical system for turbulent combustion. It is naturally closed, so we can actually directly solve the chemical mechanism, regardless it's a detailed mechanism or reduced mechanism. So that's the second step. We solve the chemical reactions happening inside each moving Lagrangian particles. And third of all is turbulent transport. So by knowing the velocity field from the velocity space solver, each particle will then move to the next space. And of course, there's some randomness about where it goes in the end. So this is basically about introduction of methods. So if you still have the details I'm not quite sure about, that's entirely fine. This is not the key point of this presentation. Just want to introduce this method so you can have it in the background. Okay, so let's then move on to the first topic now. Okay, the first topic that I'm going to introduce today is when we blend hydrogen and ammonia. So this work was published in 2023. So it actually contains 2 different parts. The first part is we updated and revised a reduced size. So it's a detailed mechanism, but we're trying to reduce the size of this mechanism to include as fewer species and reactions as possible, but maintain the characteristics that can actually reproduce the characteristics of laminar flame and turbulent flame and so on and so forth. So this mechanism has 22 chemical species and 102 reactions. And in order to just validate it, we tested ignition delay time, we tested selective non-reactive reduction behavior, and we tested it against laminar burning velocity. We also modeled this against the laminar flame, and they all achieved satisfactory results. And then we apply this to a turbulent flame. So the application to this turbulent flame, it is a mixture of ammonia, hydrogen, and nitrogen. This is not based on a crack ratio, but it's just a blending of nitrogen and hydrogen, and some kind of nitrogen as well. So this configuration of turbulent combustion is in a Carber configuration. The Reynolds number is at the range of the traditional hydrogen Carber flame. So it's about 23,600 up into about 24,000. So that's the relative Reynolds number. And then for this second part of the work, investigate the phase stabilization and what the NOx emission looks like, and is there a practical way of reducing NOx? So these are the different elements that we look at in this particular work. I don't think we have enough time today just to go to too much detail. So what I'm going to present today is just, first of all, we show you how this mechanism can reproduce the selective non-reactive reduction behavior using this mechanism. And the second of all, I'm going to show you these turbulent flames and the ways of reducing these NOx, and does it work? That's the first work. So the first work, let's say, can this mechanism reproduce selective non-catalytic reduction behavior? On the left-hand side, we have 4 plots. You can see this is actually NO mole fraction under different oxygen concentration. And all these dots are experimental results. There's 3 different lines based on 3 different chemical mechanisms. So we have Lin-state mechanism, global mechanism, and the current work is updated version mechanism. So the current work is actually dash dot line. So you can see that the dash dot line have reasonably good agreement for across different oxygen levels. And also there's a key feature, which is like when we have like ammonia added into the system, when the temperature is between 1,000 and 1,400, so this is a bit accurate as I written on right-hand side, 1,063 Kelvin to 1,366 Kelvin. Inside this narrow window, we just call it, it's in the temperature window of selective non-catalytic reduction temperature window. So within this window, you can see when you add ammonia, there is an evident decrease of NO. This has been used a long time ago and used in power plant and so on when they burn corn, biomass, and waste. And we trying to use the same mechanism to reduce NOx in turbulent flames, and I'm trying to see if that works as well in turbulent flame consideration. So this graph is just to show you, okay, we can reproduce the behavior inside this temperature window, and it grins while regardless of the oxygen level. And that's to say this mechanism, so we trusted behavior in selective non-catalytic reduction temperature window in a non-turbulent setting. So we're going to now go into the turbulent flame, see how it behaves. Okay, so now we apply this mechanism to a carbon flame. So carbon flame is an ultra-ignition stabilized turbulent flame. The Reynolds number is around 2,000, but not exactly 2,000. We have the Reynolds number listed in the table down here. So we have 3 different groups. You can see the first group is the traditional carbon hydrogen flame. So by the time we did this work, there wasn't the ammonia carbon flame at that moment. But sorry, I have to decline my call. Sorry about that. There's the colleague calling me. So the first group is the traditional hydrogen carbon flame. So by that time, we didn't have this ammonia carbon flame, which we have it now. So we're working on a new simulation for the carbon ammonia flame. So by that time, we numerically explored the difference of ammonia hydrogen flame and ammonia hydrogen blends. So you can see for the second group and third group, we replace some hydrogen with ammonia. For example, this case 3 that I called here, I replace 10% of hydrogen by volume with ammonia. The case number 4, replace 20% of hydrogen with ammonia by volume for the case 4, and just to say what's the difference. So let's just go on to the results section to see what it looks like. Okay, so before we see how the reduction of NOx behavior, we just look at the mean contour plots of NO and OH, see how it differs from carbon hydrogen flame is to a flame that contains 20% ammonia. First, we want to say that if we still have the same, cold flow temperature and 1,045 Kelvin, we won't be able to stabilize the flame. So for ammonia flame, we need a higher cold flow temperature in order to stabilize the flame at the similar stagnation and the similar stagnation point. This may sounds a bit vague, but I can show you in the lie plot. So in the next slide, you can get an idea what that actually means. And the second of all, you can see the plots. They look the max of OH. They varies from which is very close to, which is much closer to the burn exit for the hydrogen flame. It becomes much further downstream for the flame that contains 20% nitrogen, contain 20% ammonia. And then let's just look at the light plots and say how when we change the cold flow temperature to increase it from 1045 Kelvin up until 1600 Kelvin, how does the stabilization point varies for these ammonia and hydrogen blends? Okay, so these are these variations. So this is 3 cases. This black line is case 1 where we have 0% ammonia. Case 3 is where we have 10% ammonia. Case 4 is where we have 20% ammonia. And these circles are experiments for case 1 for the 0% ammonia. First of all, for the black lines, for the black solid lines is agrees well with the experiments for hydrogen, so which is a good starting point. And then we went on to say case 4 and case 5. By saying the similar stagnation point, I'm just trying to achieve the same curvature. It's the same same gradient of this temperature line. So it increase following the similar gradient. So if I don't increase the cold flow temperature, and the temperature profile will become much flatter. So just to say, if I want to achieve the same amount of temperature increase at the hydrogen flame, it needs a much higher cold flow temperature. And what impact it has on, for example, OH or NO species, as you can see, because we have higher cold flow temperature, and also eventually it leads to a stronger OH distribution. All of these distribution are along the burn axis. So the OH becomes larger, and then we can look at NO. Because we have 10% and 20% ammonia for case 3 and case 4, therefore we have much larger NO presenting in the flame, in these turbulent flames. The solid line is actually out of the page, because when we have no ammonia, the amount of NO produced is not comparable with case 3 and 4. So now the question comes, can we just reduce it? So within this work, we're trying to say if we operate the ammonia combustion within the range of the selective non-reduction catalytic temperature window, does it work for these turbulent flames? So we have this plot. Left-hand side is a maximum NO within the domain, while the right-hand side is the location where the flame actually, the stabilization point, where the maximum temperature actually is, and how the gradient looks like. So you can see that we have this slide pointing to the left-hand side, which means when we have, for example, when we start from a higher temperature, the TC, the x-axis means the cold flow temperature. For example, case 4, we have TC equals to 1600 Kelvin. So it starts from the point on the right-hand side, which have a relatively high amount of NO. And when we reduce the TC, we reduce the cold flow temperature, and it becomes more or less similar up until we goes inside the non-catalyst reduction temperature range, and suddenly drops to a order of magnitude when it's operating within this range. And you can see where the flame actually stabilizes, changes dramatically in the same temperature window as well. Well, it looks more or less similar when it's outside the temperature range. So therefore, when we operate this turbulent combustion of ammonia and hydrogen mixture inside the selective non-reactive catalyst window, it actually can reduce NO, and the flame is in a more distributed mode. But the problem will come what it would be the efficiency. So that's the next question that will be considered about if this more distributed combustion mode can actually sustain the efficiency. But now we are caring more about the emission and the moment. So the first one we'll look at the no. The second thing we also worry about is ammonia sleep. So about ammonia sleep, we define an integral here, just to trying to say what amount of ammonia that is left in the end of the domain. So this is the this is again the x-axis, again the burner axis. We have from x over the 0 up until x over the 200. We're just trying to say if this more distributed combustion mode can actually consume ammonia by the end of the domain. So by the integral, by doing the integration of ammonia mass fraction over the radial directions and up until the end of the domain, let's see what it looks like. And you can see even this more distributed mode, and there is a evident decline of ammonia. So ammonia is being consumed. And by the end of the domain, so it has become a very small number. So the right-hand side plot is a zoomed in version of the left-hand side plot. And you can see it has a effectively small number. And there's this is effectively consumed, but it depends on what number we want to achieve. And we can actually come up with other strategies of further mitigate that. But that is to say, this is good. This is very good already. Okay, that's basically the first work. And then we come to the second work. Second work has soot involved. The first work, we just have a mechanism, a turbulent flame simulation for ammonia and hydrogen. And the second question comes, what if when it blends with hydrocarbon fuel? Why are we doing this? What is the motivation of putting carbon back to the fuel again? So, and there are arguments to say that while burning sort of hydrocarbon fuels, it could be more friendly to the current design of engines. And also, a carbon neutral fuel has been made available. So hydrocarbon type of fuel is not necessary from fossil fuels. But therefore, this is also necessary to investigate the impact of adding ammonia into the hydrocarbon fuel and what it looks like. Why we want to investigate soot? If we're doing, even if we're not just directly doing soot formation, that we can understand soot is harmful for the health, is also the second contributors for global warming. What we're trying to do, we're trying to reduce soot as much as possible. We want to also understand the particle size distribution of soot. So why do we need particle size distribution? Why do we understand PSD, particle size distribution? It's because the size of the particles actually relevant to how toxic and how bad that is for humans' health. On the left-hand side, we have a plot, and we can see that the ultrafine particles is actually doing the worst to our health. So we just want to say how actually soot particles form, whether it forms inside a range that is unpleasant, and how different parameters change the distribution. Okay, that's the motivation of the second work. I didn't change this, but this has been published 2023 already on combustion flame. And let me just introduce the approach first. So for this work, I also include two part of research. The first part is a laminar flame. The second part is a turbulent flame. So the first part is ammonia ethylene laminar flames. The reason I'm doing ethylene is like 90% of the fundamental studies for soot formation is based on ethylene flames. So it's naturally that people want to investigate a mixture of ammonia and ethylene rather than a different fuel type. So the first investigation is I use detailed PAH chemistry to simulate a ammonia ethylene laminar flames to see how it performs and against the experiments, and trying to investigate ammonia of the impact of ammonia on soot formation. And then it comes to say how we want to simulate the same type of fuel in the turbulent combustion context. And we know that the detailed PAH chemistry consists of hundreds of species and thousands of reactions is not very realistic just to include the complete detailed pH chemistry for turbulent flames. So here what we did is we trying to use a simplified nucleation model. For this one, simplified nucleation model, we developed it for ethylene flames and ethylene flames at elevated pressures. And now we want to recalibrate it to make it work also for a blend of ammonia and ethylene. And by doing that, we will apply this simplified nucleation model to the ammonia ethylene turbulent flames. So that's the motivation of the second work, and that's how we actually did it. And so this method is again based on the joint scalar transport TPDF method, but different from the previous one is the previous one does not have soot formation, so it's not soot modeling. For this work, we have soot formation. So the soot modeling part, we use sectional model method. So the sectional models are actually being integrated into the Lagrangian particle as well. So in our Lagrangian particle, we have the mass fractions of each gas phase space, enthalpy, and also sections, different soot sections. Therefore, this is a fully coupled turbulent chemistry soot and radiation model. Now we're going to look at the results. Okay, so first of all, let's just look at the first configuration. The first configuration is we look at a laminar counterflow flame. So this left-hand side is just the plot of the experimental configurations. For this flame, it was experimentally studied by researchers and KAUST, and these are 4 flames for these laminar flames, which we call L1, L2, L3 up until L4. So you can see if you look at the second column, so it means from L1 to L4, we replace some sort of nitrogen with ammonia. So for L1, we have 25% of nitrogen by volume, but by L4, we have 0% of nitrogen by volume, but we have 25% of ammonia by volume. So that's the difference. That's how it varies from L1 to L4. So the first question is, can our detailed pH chemistry produce good agreement with this experimental laminar counterflow diffusion flame? And the result and the answer is yes. If you look at these plots, it has a lot of information on this slide. But if we just look at the left-hand side plot first, so this is a comparison between the detailed pH chemistry with experiments. So for the different flames, L1 to L4, I use different symbols to represent it, and I use different light types to represent our simulations. You can see that similar to the experiments, we have good agreement for each flame, and it also shows that when we add ammonia, the amount of soot reduces as we add in more ammonia. And the second question comes, what about our traditional numerical, our traditional one-step simplified nucleation model? Does it still work for the ammonia and ammonia and ethylene blends? So the right-hand side give out the equation just to show you what this global nucleation model actually looks like. So it assumes this is a global reaction which has a convert acetylene to A4 and hydrogen. So historically, we calibrated in different configurations for the ethylene flames. So we have a reaction rate, as you can see in the first line of this table on the right bottom. And it works very well for the ethylene flames. As you can see, if it's still ethylene and nitrogen blends, it's just L1. The solid line still agrees very well with the experiments. But while we add more ammonia, it tends to deviate from the experiments. So that's why we need to revise the rate to recalibrate it in order to use this simplified model for turbulent combustion. So what we did is we update the rate, as you can see on the right-hand side table. We update the rate based on the ammonia mole fraction, and now you can see it achieves a good agreement with the measurements regardless of ammonia concentration, and it has comparable good agreement with the detailed chemistry. That's very satisfactory. We are very happy about it. And then we have only 2 questions left now. The first one is, we can see this trend is when we add more ammonia, the amount of soot reduces. What is the key reason behind that? And the second reason is, the second thing we want to look at is, does this new recalibrated nucleation model still works for turbulent combustion? Okay, let's answer the first question first. Before we answer that first question, this is just to show you, this is based on detailed pH chemistry. This plot is just to show us how the different concentrations of ammonia and ethylene, the different ratio of these, and how that changes distribution. And left-hand side, we just define, because we have soot section models, or soot are categorized into different sizes. So when we just look at the soot sections that has a diameter about around 3 nanometer, 50 nanometer, 77 nanometers, how that actually looks. And you can see that when we have more ammonia, it means when we change from solid line to the dotted lines, we appear to have more smaller particles. While when we go into the big particles, when we add more ammonia, we seem to have smaller big particles, like the 77 part. And that's the same as the PSD. So left-hand side column is the particle size distribution, a very key thing that people look at for soot formation. X-axis is the dP, in the diameter, average diameter of the soot particle. And that's in the log scale. And you can see for the smaller particles, for the upstream, that it has these variation, which is consistent with our observation on the left-hand side, which is to say, when we have more ammonia, we have more smaller particles. Well, if you look at the right-hand side of PSD, it tends to have fewer bigger particles. So this variation is to say, although overall we have fewer soot formed as we add ammonia, the change among big particles and small particles are entirely different. And also, let's say, why does soot affect the production of the overall production of soot? What's the key mechanism behind it? And our first intuition would be, is that about oxidation? Is that should we have more oxidation that leads to less soot formed? And so that's why we need to look at this plot. So left-hand side, we have a left-hand side plot which plots all the major sources for oxidations for soot. And the biggest contribution, I would say, is from OH. And all the rest are very similar and collide to each other. We can't really tell the difference. So not going to talk about them. So just look into the oxidation of soot because of OH. Right-hand side is the OH oxidation rate for the 4 flames. The light type is still the same as we had before. So the solid line is where we may have no ammonia at all. The dot line is 25% ammonia. As you can see, we actually have oxidation, soot oxidation actually reduces when we increase more ammonia. You can see the oxidation rate the magnitude reduces as we add ammonia. Therefore, the oxidation is not the contribution of reducing ammonia. So what could that be? So what could be the driven mechanism behind it? And then we went on to study the nucleation. And x-axis is the Burner axis as well, between these counterflow. And the y-axis is the nucleation rate. Right-hand side is the zoom-in version of the left-hand side. And you can see there is some sort of difference already when we change from 0% of ammonia to 25% ammonia. There is a decrease of the peak slightly from this solid line to this dashed line. But it's not very obvious in terms of the flame width and how that's actually varies. So my question would be, is there another driving mechanism behind it? We know that soot nucleation can contribute that. Soot nucleation decreases with increasing ammonia, but is there a different reason? Is there a different driving mechanism behind the reduction of soot? And then we went on to study the surface growth. Within our surface growth model, it involves a couple of reactions, not going to go to details of it, but eventually we will generate a rate from this surface growth model. So the surface growth, within the surface growth model, a key parameter is what we call a surface growth function, what we can see on the left-hand side. On the left-hand side, you can see there is an evident decrease of peak when we have 0% ammonia, the solid line, to 25% the dotted line. And also the width narrows down as well. And the integral of the surface growth function is important to the rate of surface growth. Therefore, there is a more evident role coming from surface growth that contribute to the reduction of soot. So why can we say surface growth is reduced? What's the driving mechanism within the surface growth model? So we went inside the mechanism itself. We found the responsible reaction for this most evident variation. And we can see this is a massive change of available H radicals within the reactions when we compare L1 and L4, when we compare 0% ammonia and 25% ammonia. And H has been largely consumed in the situation L4 when you had 25% ammonia, which inhibits the formation of soot. So what actually consumes H radical then becomes our next question. And then we went on to explore the details, and then we found out, we plot out all the key mechanism that consumes H radical, and we found out this reaction, the NO2 and H, becomes one of the dominant consumption of H radical when we have 25% ammonia. Therefore, it's actually the NO2, it becomes much more in 25% ammonia case L4, that actually leads to the reduction of H radical, while the H radical reduction inhibits surface growth, and that leads to the less reduction of soot. So that's the main findings of a second work, and it looks into the simplified nucleation model. It's trying to investigate why adding ammonia reduces soot. And this becomes the last question, is just to say whether the surface growth model, whether the simplified, updated nucleation model actually works for turbulent flames. So thankfully, the KAUST group actually has a scaled down setting in homogeneous jet burners, which actually looks into the same mixture of fuel, which contains all the way from 0% ammonia to 25% ammonia, so which we call T1 to T4 in this plot. You can see the trend of reduction of soot is similar in the turbulent flame context, from this diamond up into this black triangles. This is an evident reduction. And here we applied our updated simplified nucleation model, and it can actually reproduce this trend of decrease as well, which is quite promising. And we want to say, is that still the surface growth is the most evident inside the turbulent flames? And then we plot out the surface growth function, and we found that is, again, the most evident contribution to the surface growth, to the soot reduction in turbulent flame context. You can see there's a decrease of peak, and also there is a shift of the peak soot, which shift from further downstream a bit to the upstream. When you have, if we consider from 0% ammonia to 25% ammonia, then it actually shifts a bit downstream when we look at this plot. And it's actually the same trend as the soot. As we can see, from 0% to 25% ammonia, the peak of soot also shift from further upstream to downstream. So it shows the same trend, it tells the same story, and surface growth decreases with the increasing ammonia concentration, also in the turbulent flame context. So this is like an encouraging result in turbulent flame as well. And that concludes our second work. And we're going to just introduce the last work I'm going to present today. This is one of the recent work that we are done. We actually modeling the ammonia, the crack ammonia flame at elevated pressures. So this is a turbulent non-premixed flame. The mixture is ammonia, hydrogen, and nitrogen. So ammonia here is crack and 40% or 28% ratio. So we simulated both cases. Just to make it simplify, what I'm going to present today is the 28% cracking ratio. It's because at this higher cracking ratio, we have more hydrogen, and we can look more into the impact of differential diffusion. Differential diffusion is more evident with the presence of higher hydrogen concentration, and that's why we choose 25% cracking ratio rather than 40 cracking ratio. The ratio of these different element is based on 28% cracking ratio. So we have this combination of ammonia, hydrogen, and nitrogen. Under the experiment condition, the pressure is at 5 atmosphere, and the temperature of the fuel is at 294 Kelvin. So it's basically room temperature. The Reynolds number here is 11,200. So it's much lower than the copper flame. So just to say, here we just say if the differential diffusion impact can play a bigger role for these turbulent flames. So why we're doing elevated pressure is because, as obvious, is the practical application features higher pressures. 5 bar is not that enough, but it's in that direction as to investigating the impact. Okay, so here, before I show you the results, just to show you what we did within our model. So just like I just mentioned, for the transported PDF method models, we used moving Lagrangian particles, which contains 3 different elements: the molecular mixing in composition space, chemical reactions, and turbulent transport. Within this model, one of the key parameters that we look at in this work is the last term on the right-hand side. The last term on the right-hand side, we normally solve it directly by molecular mixing in composition space model. So, but this is, we did this under the high Reynolds number assumption. So we actually neglect the first term of the second equation. We just did a modeling for the second term of this equation. But effectively, if we revoke the high Reynolds number assumption for this equation, we still need to model the first term. So there is another model for this first term, actually. So the first term, there's a model called molecular transport in physical space. This model was first developed by Stephen Popp's group from the US. And here we integrate this model into our code and to represent the impact with complete differential diffusion impact, because we neglect we revoke the assumption of high Reynolds number. Okay, so I just mentioned that we actually solve in the Lagrangian particles. So the composition space varies because of the transported PDF model. So therefore, we have an additional step in order to calculate this molecular transport in physical space. So for our simulations in this work, we now just have 3 steps. We have 4 steps now. We have additional step, which we call MTPS. It's just a molecular transport in physical space, which consider the complete version of this right-hand, the last term of this transported PDF method in order to consider the impact of differential diffusion. So that's an introduction of what the model changes for this work. And then let's look into the work. Let's look into how the comparison looks like. And we have, this work is actually not been published yet. It's currently under review in Combustion Flame. So the left-hand side, we have a mean temperature and RMS temperature. Right-hand side, we have the mean hydrogen mass fraction and the RMS of hydrogen mass fraction. So the black line is EMST. EMST is one of the molecular mixing model, and MTAPS is the additional term that we added in order to evaluate the differential diffusion. So black line is where we have the full model, and the red line is where we neglect MTPS, where we have EMST only. So if you look at the left-hand side first, so does it quite make a difference for the temperature? I would say the answer is not quite. For the mean temperature, you can't actually see too much difference in terms of mean temperature, but for the RMS and temperature, there's not too much difference for the x over d equals 10 or 20 is not much difference. For 40 or 60, seems there is a decrease when we add of RMS of temperature when we add MTPS, and this could be because of some additional some additional terms that we added into the enthalpy correction that affect that. But that's not bringing a better prediction when we look at the black line, but that isn't non-favorable for all the other mass fractions. So let's look at the right-hand side. Right-hand side is for the hydrogen mass fraction. So if we look at the mean first, the left-hand side, when we varies from x over d 10, 20, 40, up until 60, and we can see there is some difference began to show and x over d equals 40. Well, when it's 10 and 20, it becomes more or less the same. Well, when it's equals x over d 20, you can see there is the additional term from TPS, increased mixing, that gives us a better prediction of hydrogen mass fraction from x over d equals 40. And for the RMS of hydrogen, we can see the same trend. It's very similar upstream, but it becomes improves the prediction for up from x over t equals 40. So this is for the downstream when the turbulence is more reduced, and the flame structure tends to subjective to a tendency to have local extinction, but it's not showing a great extinction for this flame. And we want to look into other species as well. And it does not show too much difference for other species. As we know, the differential diffusion is most evident for hydrogen, not for other flame, not much for other species. So left-hand side, we have mean and RMS of ammonia. Right-hand side, we have mean and RMS of water. You can see the difference between the two the model and the model addition are quite similar. Can't really tell too much difference, but it's encouraging. It agrees well with experiments. So we have a good prediction of hydrogen on the previous slide, and we can see we have good prediction of ammonia on this slide. And a good prediction of both suggests that we have an adequate balance within our ammonia mechanism. And for this work, we use the same mechanism that we developed in the first work. And now we have an updated mechanism, but this one is based on the work that I just presented as first part of this presentation. And then let's go on and to talk about, does this MTPS have some other impact? So for transported PDF method, we have like Lagrange particles which move around the flow domain. So we can actually look at how these different particles, how they move in different spaces and how they shows the different properties. Therefore, we can actually do a lot of statistics. One of the statistics people often do is to say how the different particle statistics looks in the mixture fraction space. So this one is the temperature scatters in the mixture fraction space colored by hydrogen mass fraction. So the colors of mass fraction, and the right-hand side column just we didn't color it because that's experiments. And the first 4 columns are our simulations. The last column shows that for the current experiments, this flame, the 25% crack ammonia, it doesn't show a strong local extinction. It burns comparatively strongly across different axial locations. Therefore, we compared 2 different molecular model, which is called MC and EMST, and we found EMST has better prediction for this flame, which burns very strongly. And we know that the MC model historically tends to overpredict local extinction because of the nature of that model. And it still shows the same trend for this flame. You can see there's a lot of deviations from the mean. The mean is the red line. The black line is the mean of the simulation, and the red lines are the experiment's mean, and it was put onto different simulation results as well. You can see if there are scattered deviations from the mean, which suggests MC overpredicts the local extinction. And the second thing we want to look at is, does adding MTPS change this behavior, and how does it affect different mixing models? We can see when we have MTPS, it tends to have bigger perturbation from the fuel rich side, and then it starts to impact the fuel lean side. So it does the same for EMST. So as you can see, for the original EMST model for this flame, you can't even see too much deviation. It seems all the points are aligned perfectly with the line. But when you have EMST, it tends to have more perturbations along this mean. And so that's the extra perturbation because of the additional mixing from the MTPS. And another thing that I noticed is that for example, for MC, we have additional scatters that fall outside of this main line, which is not that true physically. We can't really have that too many points for beyond the adiabatic temperature condition. So, but when we have MTPS, these odd scatters tends to disappear, which is a pleasant thing. So we want to know if that's still true for other species. And then we have another plot here for hydrogens, because we know the impact is most evident for hydrogen. So this is the scatter plot of hydrogen scatters, again, in the mixture fraction space. And this time it was colored by temperature. And you can see these 3 columns for MC plus MTPS, and EMST plus MTPS. So we have the right-hand side is because the right-hand side so far have the best agreement with the experiments. On the left 2 columns, we want to compare the impact of MTPS. We can see the same, because for example, the first column at X over dx40, we have a lot of scatters that deviates from the mean hydrogen mass fraction. Well, when we have MTPS, all these scattered deviates from the main this main line seems to reduce quite a lot. So we actually use the equations on the right-hand side, just want to characterize how big the impact actually is. This MC model has a characteristic that people don't like, is that it has this non-locality in mixture fraction space. It means it can grab 2 particles a very far away in mixture fraction space and artificially mix them together. This is to say, can adding MTPS mitigate that negative point of model? So we can see we define how these chosen 2 particles, A and B, are different in the mixture fraction space, and how this pair is different in terms of hydrogen mass fraction. So now in this table, we compare MC and MC plus MTPS. You can see for both parameters, you can see an evident decrease when we add MTPS. So this is to say, by adding this MTPS, it produce a positive impact about the modeling using the molecular course of the MC model, because it mitigates the impact of non-locality in mixture fraction space. And although it does not predict as good results as EMST for this flame. And then it comes to say, okay, so key focus, the differential diffusion. So where does the differential diffusion actually plays a role? We have this.
Sorry to interrupt you. If you can conclude in the next couple of minutes, please.
Yeah, we are. Yeah, thank you for reminding me. We're gonna have 4 more slides, and then we're gonna finish.
Okay. Okay. Yeah. Thank you.
Thank you. The differential diffusion parameter is the one the experimentalists and also other colleagues who did simulation also look at as well. This is to say we have good agreement with the experiments, but the question is, does the differential diffusion only important for upstream than downstream? And the answer is no, because we look at the radial plots already. Here we look at PDFs and the center line and also the location of peak temperature. You can see there, although it's not that big difference, but you can see this deviation from this red light to black eye, which improves the prediction of PDF and temperature and hydrogen when we have this fully consideration of differential diffusion. And we also, the last thing we did is we numerically explored further elevated pressure and 10 or 20 pressure. You can see even at this even higher pressure, even the profiles of hydrogen can see a big difference than 20. So, and PDF, which you can see a big difference, not just at the location of peak temperature, also at the location of the center line. Therefore, when we have even further elevated pressure, the impact of differential diffusion is not neglected. So that concludes all the 3 works that I'm going to talk about today. And that's the conclusions that I made here. So first of all, the first work that I introduced a reliable HNO mechanism, and I present how the SNCR window can actually affect the NOx emission. And the second work, we look into the blend of ammonia, ethylene, and nitrogen flame. And we look into how we can actually update soot nucleation model and how we actually apply it for turbulent flames, and what is the driven mechanism behind the reduction of soot due to ammonia substitution. And the last work, we look into simulation of cracked ammonia flame, a turbulent cracked ammonia flames. And we look at the impact of differential diffusion similar to the experimental condition and also at further elevated conditions. And we found that is very important, especially at even further elevated conditions. So just as to say, to model ammonia flames, combustions, we look into different pollution elements, emission elements. There are a lot of things that we need to play around the temperature. Lower temperature helps NOx, and like the NO2 elements can actually reduce soot. So there is actually a play around between NOx, soot, and the efficiency of the whole system that people need to look at in the future for ammonia combustion. So that's the major conclusions and takeaways for today's presentation. And last but not the least, I want to thank all the people that have helped me in the 3 works from Imperial College and also from KAUST, and also thank the sponsors for EOARD, EPSRC, and Loughborough University. And thank you so much. And if you have any question, I would like to take your question. Thank you.
Thank you. Thank you very much, Lu, for this very interesting, dense talk. Now it's, yeah, like you said, it's time for questions. So if everyone from the audience would like to ask a question, please free to raise your hand virtually or unmute yourself. Well, maybe I'll start with a question. I was wondering, maybe I missed it, if you had quantify how much the reduction of soot that you showed us is related to the fact that there are less carbon molecules, there is less hydrocarbons available due to the fact that you increase the ammonia in the fuel. So if you
yeah, actually we look at that as well, and there are 2 different. There actually these experiments was did not just for hydrogen, also for substitution of hydrogen. So they substitute some with ammonia. The other case is substitute with hydrogen. And what people found is that if we have less hydrogen, theoretically, we will have less soot for both hydrogen substitution and ammonia substitution, because anyway, this carbon element, we have less carbon element. But the thing is, we only have less soot when we add ammonia, but we tend to have more soot formed when we add hydrogen. So we have actually looked into the other work just to say, when we add ammonia, it actually promotes surface growth that leads to more soot form. So although it has less carbon element available, but it's more driven by the mechanism of soot formation.
Okay.
I hope that can answer your question.
Yeah. Thanks. It did. Thanks. And are there any other questions from the audience? Well, if not, I've just like a curiosity. I'd like to ask you your opinion about this transported PDF models, which is very precise, very detailed, but I'm guessing it's quite time-consuming. CPU in terms of computational costs are very high. What do you think? Especially in industry and application side of things. So would you see, like in the next future, that more industry will actually adopt transported PDF thanks to increase of computational efficiency, increase of parallelization and so on? Or you still think that this model is more for getting more kind of recluded in a way in the academia world rather than industrial? Just curiosity.
Yeah, thank you for your question. I think if at the current form, if we just look at dense, so when we call dense, it means we have hundreds of particles in one cell. When we calculate dense transported PDF, if we don't change anything at all, I think it will take a really long time in order to use it for a practical applications, for example, a gas turbine or things like that. So it's a far way to go, even if we have like more computational resources. But first of all, it's a good method. It produces really good phenomenon. That's the key point. And the other thing is like we can actually develop it to actually facilitate the needs of calculating practical applications. For example, I think the sparse PDF method is like what people have used for MMC and so on. That's a good method. Actually, that's maintains the characteristics of the transported PDF method, like solving the chemical reactions naturally, but yet you use less particles across the field. So that brings it closer to the applications and the real industrial applications. So that's the key point. It has less particle, presents accuracy. And the second thing I think is to, in combination of AI technologies, that will be a future of transported PDF. Again, this is what I'm trying to work on as well. My motivation is that what if I like make a surrogate model that based on transported PDF method, would it give a better result or not? So it's something that I'm working on at the moment.
Okay, nice. Something more efficient than Monte Carlo sampling, something more computationally efficient. Okay, thank you. I see that Alessandro. Do you have a final remark, Alessandro? Okay.
No remarks. I was listening to the answer, and this is exactly what I wanted to ask, so that's fine.
Okay, then I guess we can conclude the Q&A session. Thank you very much, Liu, for your time and for preparing.
Thank you very much. Thanks.
Delivering this presentation.
Thank you both for your invitation and organizing the event. It's really pleasant to join here. Yeah, thank you so much. Thank you for your audience for attending.
Thank you very much.